Equalization is the process of adjusting the balance between frequency components within an electronic signal. The most well-known use of equalization is in sound recording and reproduction, but there are many other applications in electronics and telecommunications. The circuit or equipment used to achieve equalization is called an equalizer. These devices strengthen or weaken the energy of specific frequency bands. In sound recording and reproduction, equalization is the process commonly used to alter the frequency response of an audio system using linear filters. Most hi-fi equipment uses relatively simple filters to make bass and treble adjustments. Graphic and parametric equalizers have much more flexibility in tailoring the frequency content of an audio signal. An equalizer is the circuit or equipment used to achieve equalization. Since equalizers adjust the amplitude of audio signals at particular frequencies, they are, in other words, frequency-specific volume knobs. In the field of audio electronics, the term equalization has come to include the adjustment of frequency responses for practical or aesthetic reasons, often resulting in a net response that is not truly equalized. The term EQ specifically refers to this variant of the term. Stereos typically have adjustable equalizers which boost or cut bass or treble frequencies. Broadcast and recording studios use sophisticated equalizers capable of much more detailed adjustments, such as eliminating unwanted sounds or making certain instruments or voices more prominent. Equalizers are used in recording studios, radio studios and production control rooms, and live sound reinforcement to correct the response of microphones, instrument pickups, loudspeakers, and hall acoustics. Equalization may also be used to eliminate unwanted sounds, make certain instruments or voices more prominent, enhance particular aspects of an instrument's tone, or combat feedback in a public address system. Equalizers are also used in music production to adjust the timbre of individual instruments by adjusting their frequency content and to fit individual instruments within the overall frequency spectrum of the mix. The most common equalizers in music production are parametric, semi-parametric, graphic, peak, and program equalizers. Graphic equalizers are often included in consumer audio equipment and software which plays music on home computers. Parametric equalizers require more expertise than graphic equalizers, and they can provide more specific compensation or alteration around a chosen frequency. This may be used in order to remove a resonance, for instance. Terminology. The concept of equalization was first applied in correcting the frequency response of telephone lines using passive networks. This was prior to the invention of electronic amplification. Initially, equalization was used to compensate for the uneven frequency response of an electric system by applying a filter having the opposite response, thus restoring the fidelity of the transmission. A plot of the system's net frequency response would be flat, as its response to all frequencies would literally be equal. Hence the term equalization. Much later the concept was applied in audio engineering to adjust the frequency response in recording, reproduction, and live sound reinforcement systems. Sound engineers correct the frequency response of a sound system so that the frequency balance of the music as heard through speakers better matches the original performance picked up by a microphone. Audio amplifiers have long had filters or controls to modify their frequency response. These are most often in the form of variable bass and treble controls, and switches to apply low-cut or high-cut filters for elimination of low-frequency rumble, and high-frequency hiss respectively. Graphic equalizers and other equipment developed for improving fidelity have since been used by recording engineers to modify frequency responses for aesthetic reasons. Hence in the field of audio electronics the term equalization is now broadly used to describe the application of such filters regardless of intent. This broad definition therefore includes all linear filters at the disposal of a listener or engineer. A British EQ or British-style equalizer is one with similar properties to those on consoles made in the UK by companies such as Amec, Neve and Soundcraft from the 1950s through to the 1970s. Later on, as other manufacturers started to market their products, these British companies began touting their equalizers as being a cut above the rest. Today, Many non-British companies such as Behringer and Mackie advertise British EQ on their equipment. A British-style EQ seeks to replicate the qualities of the expensive British mixing consoles. History: filtering audio frequencies dates back at least to the harmonic telegraph and multiplexing in general. Audio electronic equipment evolved to incorporate filtering elements as consoles and radio stations began to be used for recording as much as broadcast. Early filters included basic bass and treble controls featuring fixed frequency centers, and fixed levels of cut or boost. These filters worked over broad frequency ranges. Variable equalization in audio reproduction was first used by John Vokerman working at RCA in the 1920s. That system was used to equalize a motion picture theater sound playback system. The Langevin model EQ251A was the first equalizer to use slide controls. It featured two passive equalization sections, a bass shelving filter, and a pass-band filter. Each filter had switchable frequencies and used a 15-position slide switch to adjust cut or boost. The first true graphic equalizer was the Type 7080 developed by Art Davis's Cinema Engineering. It featured 6 bands with a boost or cut range of 8 decibels. It used a slide switch to adjust each band in 1 decibel steps. Davis's second graphic equalizer was the ALTEC Lansing Model 9062 AEQ. In 1967 Davis developed the first January 3rd octave variable notch filter set, the ALTEC Lansing Acoustic Voice System. Daniel N. Flickinger introduced the first parametric equalizer in early 1971. His design leveraged the high-performance op-amp of his own design, the 535 series, to achieve filtering circuits that were before impossible. Flickinger's patent from early in 1971 showed the circuit topology that would come to dominate audio equalization until the present day, as well as the theoretical underpinnings of the elegant circuit. Instead of slide potentiometers working on individual bands of frequency, or rotary switches, Flickinger's circuit allowed completely arbitrary selection of frequency and cut boost level in 3 overlapping bands over the entire audio spectrum. 6 knobs on his early EQs would control these sweepable filters. Up to 6 switches were incorporated to select shelving on the high and low bands, and bypassing for any unused band for the purest signal path. His original model boasts specifications that are seldom met today. Other similar designs appeared soon thereafter from George Massenburg and Burgess McNeil from ITI Corporation. In May 1972 Massenburg introduced the term parametric equalization in a paper presented at the 42nd Convention of the Audio Engineering Society. Most channel equalization on mixing consoles made from 1971 to the present day rely upon the designs of Flickinger, Massenburg and McNeil in either semi or fully parametric topology. In the late 1990s and in the 2000s, parametric equalizers became increasingly available as digital signal processing equipment, usually in the form of plugins for various digital audio workstations. Standalone outboard gear versions of DSP parametric equalizers were also quickly introduced after the software versions and are typically called digital parametric equalizers. Filter types. Although the range of equalization functions is governed by the theory of linear filters, the adjustment of those functions and the flexibility with which they can be adjusted varies according to the topology of the circuitry and controls presented to the user. Shelving controls are usually simple first-order filter functions which alter the relative gains between frequencies much higher and much lower than the corner frequencies. A low shelf, such as the bass control on most hi-fi equipment, is adjusted to affect the gain of lower frequencies while having no effect well above its corner frequency. A high shelf, such as a treble control, adjusts the gain of higher frequencies only. These are coarse adjustments more designed to increase the listener's satisfaction than providing actual equalization in the strict sense of the term. A parametric equalizer, on the other hand, has one or more sections each of which implements a second-order filter function. This involves 3 adjustments: selection of the center frequency, adjustment of the Q which determines the sharpness of the bandwidth, and the level or gain control which determines how much those frequencies are boosted or cut relative to frequencies much above or below the center frequency selected. In a semi-parametric equalizer there is no control for the bandwidth or is only selected between two presets using a switch. In a quasi-parametric equalizer, the bandwidth is depending on the gain level. With rising gain, the bandwidth gets wider. A graphic equalizer also implements second-order filter functions in a more user-friendly manner, but with somewhat less flexibility. This equipment is based on a bank of filters covering the audio spectrum in up to 30 frequency bands. Each second-order filter has a fixed center frequency and Q, but an adjustable level. The user can raise or lower each slider in order to visually approximate a graph of the intended frequency response. Since equalization in the context of audio reproduction isn't used strictly to compensate for the deficiency of equipment and transmission channels, the use of high and low-pass filters may be mentioned. A high-pass filter modifies a signal only by eliminating lower frequencies. Thus a low-cut or rumble filter is used to remove infrasonic energy from a program which may consume undue amplifier power and cause excessive excursions in speakers. A low-pass filter only modifies the audio signal by removing high frequencies. Thus a high-cut or hiss filter may be used to remove annoying white noise at the expense of the crispness of the program material. A first-order low or high-pass filter has a standard response curve which reduces the unwanted frequencies well above or below the corner frequency with a slope of 6 dB per octave. A second-order filter will reduce those frequencies with a slope of 12 dB per octave and moreover may be designed with a higher Q or finite zeros in order to effect an even steeper response around the cutoff frequency. For instance, a second-order low-pass notch filter section only reduces very high frequencies, but has a steep response falling to zero at a specific frequency. Such a filter might be ideal, for instance, in completely removing the 19 kHz FM stereo subcarrier pilot signal while helping to cut even higher frequency subcarrier components remaining from the stereo demultiplexer. In addition to adjusting the relative amplitude of frequency bands, an audio equalizer may alter the relative phases of those frequencies. While the human ear is not as sensitive to the phase of audio frequencies, music professionals may favor certain equalizers because of how they affect the timbre of the musical content by way of audible phase artifacts. High-pass and low-pass filters equals, a high-pass filter is a filter that passes higher frequencies well but attenuates lower frequency components. A low-pass filter passes low-frequency components of signals while attenuating higher frequencies. In audio applications these are frequently termed low-cut and high-cut respectively, to emphasize their effect on the original signal. For instance, sometimes audio equipment will include a switch labeled high-cut, or described as a hiss filter. In the times of phonographs, many stereos would include a switch to introduce a high-pass filter, often called a rumble filter, to eliminate infrasonic frequencies. Shelving filter equals, while high and low-pass filters are useful for removing unwanted signal above or below a set frequency, shelving filters can be used to reduce or increase signals above or below a set frequency. Shelving filters are used as common tone controls found in consumer audio equipment. These implement a first-order response and provide an adjustable boost or cut to frequencies above or lower than a certain point. A high shelf or treble control will have a frequency response H, F, whose square is given by where Fp and Fz are called the pole and zero frequencies, respectively. Turning down the treble control increases Fz and decreases Fp so that frequencies higher than Fp are attenuated. Turning up the treble control increases Fp and decreases Fz so that frequencies higher than Fz are boosted. Setting the treble control at the center sets Fz equals Fp so that H, F, 2 equals 1 and the circuit has no effect. At most, the slope of the filter response in the transition region will be 6 dB per octave. Similarly, the response of a low shelf or bass control can be represented as. In this case, the inclusion of the leading factor simply indicates that the response at frequencies much higher than Fz or Fp is unity and that only bass frequencies are affected. Note that a high shelf in which Fz is set to infinity or a low shelf response in which Fz is set to 0 implements a first-order low-pass or high-pass filter respectively. However, usual tone controls have a more limited range, since the purpose isn't to eliminate any frequencies but only to achieve a greater balance when, for instance, the treble is lacking and the sound isn't crisp. Since the range of possible responses from shelving filters is so limited, they are considered quite inadequate for equalization tasks among audio engineers. Graphic equalizer equals. In the graphic equalizer, the input signal is sent to a bank of filters. Each filter passes the portion of the signal present in its own frequency range or band. The amplitude passed by each filter is adjusted using a slide control to boost or cut frequency components passed by that filter. The vertical position of each slider thus indicates the gain applied at that frequency band, so that the knobs resemble a graph of the equalizer's response plotted versus frequency. The number of frequency channels affects the cost of production and may be matched to the requirements of the intended application. A car audio equalizer might have one set of controls applying the same gain to both stereo channels for convenience, with a total of 5 to 10 frequency bands. On the other hand, an equalizer for professional live sound reinforcement typically has some 25 to 31 bands, for more precise control of feedback problems and equalization of room modes. Such an equalizer is called a 1/3 octave equalizer because the center frequency of its filters are spaced 1/3 of an octave apart, 3 filters to an octave. Equalizers with half as many filters per octave are common where less precise control is required. This design is called a 2/3 octave equalizer. Parametric equalizer equals. Parametric equalizers are multi-band variable equalizers which allow users to control the 3 primary parameters, amplitude, center frequency and bandwidth. The amplitude of each band can be controlled, and the center frequency can be shifted, and bandwidth can be widened or narrowed. Parametric equalizers are capable of making much more precise adjustments to sound than other equalizers, and are commonly used in sound recording and live sound reinforcement. Parametric equalizers are also sold as standalone outboard gear units. A variant of the parametric equalizer is the semi-parametric equalizer, also known as a sweepable filter. It allows users to control the amplitude and frequency, but uses a preset bandwidth of the center frequency. In some cases, semi-parametric equalizers allow the user to select between a wide and a narrow preset bandwidth. Filter functions. The responses of linear filters are mathematically described in terms of their transfer function or, in layman's terms, frequency response. A transfer function can be decomposed as a combination of first-order responses and second-order responses. These can be described according to their so-called pole and zero frequencies, which are complex numbers in the case of second-order responses. First-order filters equals. A first-order filter can alter the response of frequencies above and below a point. In the transition region, the filter response will have a slope of up to 6 decibels per octave. The bass and treble controls in a hi-fi system are each a first-order filter in which the balance of frequencies above and below a point are varied using a single knob. A special case of first-order filters is a first-order high-pass or low-pass filter in which the 6 decibels per octave cut of low or high frequencies extends indefinitely. These are the simplest of all filters to implement individually, requiring only a capacitor and resistor. Second-order filters equals. Second-order filters are capable of resonance around a particular frequency. The response of a second-order filter is specified not only by its frequency but its Q. A higher Q corresponds to a sharper response around a particular center frequency. For instance, the red response in the accompanying image cuts frequencies around 100 Hz with a higher Q than the blue response, which boosts frequencies around 1000 Hz. Higher Qs correspond to resonant behavior in which the half power or -3 decibels bandwidth, BW, is given by, where FO is the resonant frequency of the second-order filter. BW is the bandwidth expressed in the same frequency unit that FO is. Low Q filter responses where Q,